LLM, latency is silently draining your system resource. Here's why. In this guide, we explore how LLM inference latency disrupts traditional circuit breaker patterns, the risks of ignoring slow responses in production, and practical adaptations specifically for Node.js services handling LLM calls. Traditional breakers only trip based on error counts, completely ignoring latency as a failure mode. Slow LLM calls consume resources and cause queue buildup before breakers activate, severely degrading overall service availability. LLM latency delays the arrival of error signals, causing breakers to remain closed during slow calls. This leads to resource exhaustion, thread starvation, and cascading failures downstream in the system architecture. To improve circuit breakers, monitor latency metrics alongside errors, set explicit latency thresholds, and implement dynamic resets so breakers adapt in real time to variable LLM response times and prevent overload. Latency-aware breakers trip when observed response times exceed configured thresholds, preventing system overload during slow LLM inference, rather than relying solely on error counts to trigger breaks. Combining latency measurements with failure counts creates a dual-metric breaker that balances sensitivity to slow responses and actual errors, improving detection accuracy and reducing false positives in production. Use sliding windows to track recent latency and failure events continuously, allowing breakers to adapt sensitivity based on current traffic patterns and dynamic LLM behavior fluctuations in production. Sliding window breakers collect time-stamped latency samples and prune entries older than the configured window, maintaining an up-to-date latency distribution for accurate real-time breaker decisions. Runtime configuration enables dynamic adjustment of breaker parameters like latency thresholds and window sizes, allowing teams to respond quickly to changing LLM latency patterns without requiring service redeployment. Centralize breaker configurations in a config store, enable hot reloads for immediate effect, and expose detailed latency and state metrics through monitoring dashboards to improve operational visibility and troubleshooting. Example code demonstrates updating latency thresholds at runtime and logging breaker state changes, supporting operational tuning and configuration changes without requiring downtime or redeployment. Testing breaker resilience requires simulating slow LLM responses and validating breaker trips under latency stress, detecting hidden failures before deploying to production environments. Inject variable response delays in tests, monitor breaker state transitions, and automate failure scenarios to ensure comprehensive validation of latency resilience under diverse LLM conditions. This test simulates a slow LLM call exceeding the latency threshold and asserts that the breaker opens, preventing system overload and protecting downstream services effectively. Human review of breaker logs enables tuning latency thresholds by balancing false positives and false negatives, optimizing system availability and reducing unnecessary downtime caused by overly sensitive breakers. Log detailed latency and failure metrics continuously. Schedule regular reviews of breaker performance and automate configuration updates to continuously refine breaker behavior and maintain system stability. Enhanced breaker logs include latency distributions and failure counts, supporting data-driven tuning and enabling faster incident response by providing rich context on breaker trips and system behavior. Deploying refined breakers requires close collaboration between development, operations, and monitoring teams to ensure smooth rollout, continuous monitoring, and rapid rollback if unforeseen issues occur in production. In summary, traditional breakers fail under LLM latency. Use latency-aware dual metrics, sliding windows, runtime configs, thorough testing, and human reviews to maintain system stability. Now, identify latency flaws in your own breaker implementations.